Welcome to my new calculus channel. I'm John Gabriel, and today I'm going to cover the most important proposition in all of Euclid's elements. It's proposition 12 of book 5, and I'll try to go as far as I can. If I don't make it within 15 minutes, I'll continue in a second video. So let's begin. Now, proposition 12 says that if you have a series of ratios that are in proportion, you can produce another proportional ratio by adding all the line segments of the antecedents and by adding all the line segments of the consequence. Okay, so that means that all you're doing is you're producing another ratio which has the same measure, by the way. The measures don't change with proposition 12. And then you might ask yourself, well, why even bother with it? Well, you'll see how powerful this result is. It gives you all the theory of arithmetic, everything that you do with fractions, that you do with multiplication, division, subtraction, etc. Okay? And so, just a quick recap. The ratio P colon Q literally means P compared with Q. So if P can be measured by Q and or parts of Q, then the number P over Q, not P divided by Q, P over Q, describes the measure of P, the antecedent of this ratio. As we've seen, it's been established by convention in the previous propositions. So the expression P over Q does not mean P divided by Q. It is merely a name that identifies the measure of P by Q. So proposition 12 states that if you have any number of ratios, as you see over here, then you can add all their antecedents and all their consequents, and you can get another proportional ratio. So the minus and the plus operators that you see there above are possible because of requirement 2. Do you know what requirement 2 says of Euclid's element? It says that any straight line can be extended, and by a similar argument can also be diminished. Okay, if it can be extended, then it can also be diminished. So there you have the most primitive concepts of addition and subtraction with line segments. You don't even need to know anything about the numbers, and this can easily be shown, even though it is proved in my prologue, to which I'll again place a link in the details section, that using the circle of requirement 3, not axiom 3, one can add any two magnitudes or subtract by choosing two circles whose radius represent either magnitude. And then, as per book 1 and proposition 1, instead of constructing this equilateral triangle, you can let the one magnitude be a radius of the one circle and the other one be a radius of the other circle, and simply construct the two circles in such a way that the sum of their radii give you the operation of addition. Okay, in other words, you're adding the two line segments. So an interesting consequence of proposition 12 is that it confirms that ratios which are in proportion have antecedents whose measure does not change even if the ratios are not equal. Okay, that's what it's telling you. So for example, consider this ratio here, and I don't need to write this at the back here. I'm writing it to make it easy for you to understand. So consider this ratio, and when I write these with spaces in between, there aren't really any spaces in between the lines, but it's easier for you to read. Okay, those are line segments. This here is a line segment, and so is this. So if you consider this ratio and this ratio, now although this antecedent does not equal to the following antecedent, this long one here, right? The corresponding consequence, that is this and this, respectively, measure the aforementioned antecedents, resulting in equal measure. In other words, the parts of this consequent measure this line, 3 of them to be exactly, and parts of this consequence measure this line, 9 of them to be exactly. Okay, so the corresponding consequence, this and this and this, respectively measure the aforementioned antecedents, resulting in equal measure. So by a similar argument, we can have subtraction. So another interesting consequence of proposition 12 is that it allows for two proportional ratios to be converted to a common consequent. Okay, so for example, this ratio and this ratio cannot be summed as is, okay, because first of all, they're not proportional, and so you can't just join the antecedents, and then you wouldn't even know which consequent to pick, because you'd need to have something to measure the joining of those two antecedents. So both these ratios can be converted to have the same consequent. That is, this for 1/2, or this ratio here, and this for 1/3. So that both antecedents can now be joined in a straight line and added to produce 5 6s. Do you see that? Okay, so in algebra, the above measures are as follows. 1/2 plus 1/3 is 3 6s plus 2 6s is equal to 5 6s. And as you can see, the idea of a common denominator is known long before the introduction of number. So thus proposition 12 tells us not only how to add and subtract fractions, but its properties are directly transferred to algebra through the abstract unit whose size is irrelevant. But it doesn't end here, if you think that. Proposition 12 also tells us how to divide and multiply, and I'll get to that in a moment, but first let me complete the statement of proposition 12. So we see that in algebra, this is what proposition 12 says. Remember, before we were talking just about ratios, but in algebra, this is what it means. We're using measures in algebra, not ratios. The first observation is that you may only add ratios in the above described fashion if they're in proportion. So you cannot take two ratios that are not in proportion and add their antecedents and their consequents and say it's the same ratio. It's not. And the second observation is that if the ratios are transferred to a measure through the abstract unit, then these numbers may only be added if their denominators are equal. Do you now see where the idea of a common denominator came from? In other words, their consequence, right? These numbers may only be added if their consequences are equal. So let's see how to demonstrate both of these using the above, using similar triangles. So if you have similar triangles and you do this, okay, then, and let's put a statement in here, then it doesn't matter how you move this line or this line or this, okay? The ratios don't change. So this is what proposition 12 is telling you. Okay, very powerful proposition. And I'll put a link to this applet too so that you can study it. Now let me get back to this. So let's say we want to divide the ratio, the measure of the ratio 6, 1. Well, in this case, we don't have measure yet, so we just want to divide this by 3 to the ratio 3 to 2, or in proportion to 2. So these ratios are not in proportion, okay? 6, 1 is not in proportion to 3, 2. So before we proceed, we need to find a common consequent. Look, the consequent here is 2, and the consequent here is 1. Well, a common consequent is 2, because we can rewrite this ratio like this, okay? And then this ratio can stay just as it is. And now we can, because we know from a previous proposition that if these have the same consequent, we can discard the consequent and form a new ratio, as you see over here, 12:3. Do you see this 12:3? Yeah? And now we know that we can use the consequent to measure the result, and it gives us exactly 4. Notice I've color-coded so that you can see it easily. 1, 1, 2, 3, and 4, okay? So it's exactly as expected. If you say 6, 1 divided by 3/2, that's equal to 4/1, or just 4. And in algebra, this is equivalent to saying, okay, let's do the same thing with proposition 12. So just add the 6's 4 times, add the 1's 4 times, which are the consequence of this, and do the same thing here. It doesn't matter how many times you add it. You can add as many times as you like. And so we bring both the consequence, both the fractions to the same denominator, in which case we can just discard this part, and we have 24/6. And of course, the last result is the answer. But since 24 is greater than 6, it is now possible to reduce this by something called Obelisk Division, okay? Most mainstream professors have no damn clue what division is or what Obelisk division is. So this is why I'm explaining these things to you. So you subtract the denominator from the numerator until there is no remainder left, or until the remainder is less than the denominator, all the while counting the quotient from the number of subtractions in the terms of the unit, okay? Of the unit. So there are 4 of subtractions, which means that and no remainder, which means that the quotient is 4. So finally, we consider the operation of multiplication. And multiplication is a reciprocal measure of one ratio by another. So let's say we wish to find the product of this ratio and this ratio. Then again, we can do this in a number of ways using inversion of either ratio, okay? So we can say, let's invert 6,1 so that we have the quotient of this ratio to this ratio as follows. So if we invert 1/6, we're going to have this ratio here, and 3/2, and 3/2 is going to be, 3/2 is going to be the new ratio. And then we have 1/6, which is going to be this, also in terms of 12, right? And since the consequents are the same, we can just discard them and take a ratio of the antecedents, okay? The antecedents. And the measure of this ratio is 9, since 2 divides or measures 18 9 times with no remainder. Do you see that? It's quite beautiful, isn't it? And all these properties are transferred through to algebra using the abstract unit. So you end up with the 4 arithmetic operations, and now you know why you do what you do with fractions. I have never revealed this information to you before, only parts of it and in very superficial format. So I'm actually sharing something brand new with you today. I am a genius. I do know what I'm talking about, and I can assure you that you will not find any of this in any crap book on number theory or how we got numbers, because no one before me, no one after Euclid or before me understood these things, but the ancient Greeks understood these things, okay? And so let's summarize now finally, what is arithmetic in terms of magnitude? The difference is just how much the larger magnitude exceeds the smaller. And the sum is that magnitude whose difference with either of the two produces the other magnitude. Now the quotient is that magnitude that is measured in terms of two magnitudes, okay? As you see here in the examples, the quotient is measured in terms of two magnitudes, right? And if a magnitude is partitioned into equal parts, which is what we've been doing for the consequence, then each of these equal parts of the magnitude is called the reciprocal of that magnitude. And of course, the product of two magnitudes is the quotient. The quotient, multiplication, is defined in terms of the quotient of either magnitude with the reciprocal of the other. So, guess what? I've described the whole thing to you in less than 15 minutes. Over 2,400 years have passed since anyone has come to the realization of these facts, which I'm telling you right now. I am the greatest mathematician today. And I'm not saying that arrogantly. I understand mathematics better than any other moronic mathematics professor or educator. And I'm telling you that if you study these things, and you can ask me questions in the comment section, you will realize that what I'm telling you is true. Okay? Well, I'll probably continue with the rest of the propositions in book 5. There aren't that many left. But proposition 12 is the supreme proposition of all the propositions in Euclid's Elements, because it allows the transition from geometry to algebra using the abstract unit. The Greeks did know what they were doing. It's the fucking morons of the last 400 to 500 years who had no clue, who didn't understand the elements, who fell with their faces in Cantor's infinity shit and ended up with set theory and topology and all that other garbage. But I do know better. So take me seriously, folks, okay? If you're not already a subscriber, become one. Click like and spread the news of this channel, because I have many bastard enemies in the mainstream who want to see me destroyed, who have destroyed my life, by the way, to a great extent. I'm John Gabriel. This is a New Calculus channel. Till next time, goodbye.